The topic of today's panel is what do computational scientists need from computer scientists? And unfortunately, the phrase computational scientist has kind of gotten a little schizophrenic lately. Many people use computational scientists to mean, computer scientists, just plain computer scientists that happen to be talking to the scientists. They say, oh, we are scientists and these guys are computational scientists. That's not the sense in which I mean that phrase. There is, several years ago, this idea came in vogue that said that science is now done in, in maybe 3 flavors now instead of 2. There was experimental science. Pete, I'm going to take a few minutes, so if you want, feel free to sit down. Science is done experimentally. So there is experimental science, then theoretical science. Those were the 2 main branches of science. And then it turns out, well, then now there is a third branch, which is computational science. In some sense, the branching off of theoretical science. One of the famous, and I'm mixing up names, so I won't say the name, one of the famous early 20th century quantum mechanists said that all the problems in physics are now solved and all that remains is calculation. And it turns out that was right, but the emphasis about all that remains was the problem. There's a lot of calculation that needs to be done before we can predict from the first principles. So then the branch of computational science is actually to do with predicting using computation or validating using computation. And so this is the sense in which I use the word computational science here. Scientists basically who are using computation for their purposes. Traditionally, scientists develop codes in their labs. These were typically, physicists, chemists, other science and engineers, and oftentimes these were what you would call Renaissance people within those labs. People who were not just comfortable with equations, but could also think about coding, and those people wrote the initial codes. As the computers became more and more powerful, and I'm paraphrasing some of the description that I just wrote into the web page, but for the workshop. But as the computers become more complex, programming became more complex. That kind of what started happening is that computer scientists were increasingly called upon or increasingly participated in designing, architecting, developing codes. The question is, what role should they play? What capabilities should they have? And in fact, there are some very facetious answers one can give. Actually, they're not so facetious, they're real. They actually find people saying those things. If you ask scientists, they'll say, what about computer scientists helping you? They'll say, yeah, well, these guys are like someone who has a hammer and then they keep looking for nails. They have a solution and then they're looking for problems they can solve with that solution rather than developing a solution for the problems that they have, and therefore they're not very useful people. Or another thing which is kind of different is that, computer scientists are very useful. They program for us. They write code for us. Both of those are somewhat facetious, and hopefully, in fact, the second one, sometimes scientists don't recognize as facetious. I said that's what they do, of course. But computer scientists actually think that they can contribute more by developing abstractions, and the task is to stay relevant. The question is what are the best ways in which we can do that? What kind of qualities, what kind of types of efforts we must have in the computer scientists. In particular, do we need to have the computer scientists become expert in the application domains before they can contribute, or can we figure out some way of factoring the expertise so that different people can contribute their expertise into a developing code without having to become experts in each other's domains? So those are some of the questions, and then beyond that, the panelists and you will take the theme where you want to take it. One thing I did want to exclude almost is computer scientist. I mean, usually when people say, "Oh, you are a computer scientist and you work in HPC, you must be a numerical methods guy." Well, it turns out that there are lots of people who are not numerical methods people who do computer science, and it is that computer scientist that we are talking about. And the reason for that is simply practical. And numerical methods is a very important area, And in fact, the only problem with that is that it is not controversial at all. We all agree that that is needed, and so we wouldn't have much of a discussion beyond that one sentence. Yes, that's very useful. And so that's why I don't want to emphasize or focus on that. But if there are points regarding that some of you want to make, that will be fine as well. So with this, I will turn it over to the panel, and we'll go in alphabetical. And if I mess up my alphabetical order, someone please correct me. So the first one is Pete Beckman.
Alphabetical by last name, I take it.
Yeah, alphabetical by last name. Yes.
All right. So I don't have any slides. I'm just going to mention a couple things. Let me first find out who here is a computer scientist. All right, and who here would consider themselves a computational scientist? So what? Wait, I'm confused now. All right. So yeah, I guess my perspective on what a computational scientist is, it's someone without a blackboard or a lab. They're forced to use a computer. So this issue of computational scientists and computer scientists is actually very pertinent right now, and I've been thinking about it lately, and I wanted to maybe talk about it a little bit with you guys. So I was at a very large university a couple months ago talking to their dean and the VP of research that wanted to sort of reinvigorate the computer science department at this university. The university had not done so well, and they needed some tips for moving forward. And it was very clear that there were two perspectives on campus: the computational science perspective and the computer science perspective. And these were totally disconnected. So the dean wanted to know why the computer scientists weren't working with all of the other disciplines, chemistry, physics, and everyone else. And the computer scientists in the department wanted to know why the physicists and chemists and astronomers and all that didn't want to work with them. And it came down to a difference in what each of them perceived, and Sanjay pointed out, is their basic job description. And it is the difference between being a scientist and being a programmer. So the problem was, when Sanjay joked about it at lunch, is what do computer scientists need from computational scientists? He said, well, it's only one thing: respect. And that was exactly the problem in the computer science department. They were going to physics, chemistry, and other groups, and they wanted to solve and work on problems that were computer science problems. The computational scientists saw these folks showing up and said, oh, great, programmers. So here is my code. I'm having trouble. I have a syntax error here, and I'm not quite sure how to solve this, right? And so the biggest thing I think that can help, or what do computational scientists need from computer scientists, and really vice versa, is an understanding of, the first step is an understanding of the discipline. So one of the things that's difficult about computer science is it really a science, or is it engineering, right, or is it a craft? And this is actually at the heart of the problem, and what causes most confusion here, which is that there is a lot of computer science that is complete, pure science, blackboard, proofs, concepts, new algorithms. You never need to touch a computer. In fact, there's a great quote about, computer science is, how does the quote go? The computer scientist is as much about the computer as astronomy is about the telescope, right? So the notion that we use computers, yes, but it's really about the computer science. So that's one part of our job. The second part, though, is they actually practically using the computer science, right? And that requires computers. And in some sense, it's very much like a physician. There's a set of things that a physician actually has to do in an operating room with real tools, but there actually is a science behind the body, right? So this complex reaction here is that what computer scientists want from computational scientists are challenging computer science problems. What computational scientists want from, or what they need from computer scientists, right, are solutions to computer science problems that are more than just programming. So let me give you a couple of examples of how that could work best. So recently, the community has started talking about compact apps, mini apps, skeleton apps, at least in our community. That is now the buzzword of the day. And really, these are applications that have been slimmed down until they're small enough so that a computer scientist who does not want to do the domain science can unpack it and tear it apart and use it. So the first thing that would help in the connection between computer scientists and computational scientists is these sort of applications, which demonstrate the problem trying to be solved without specifying the solution that, okay, here's where I need a programmer to write this. So that is a fantastic thing for us. The second thing that's really helpful in this communication is knowing what variables will change and plan to change. So a lot of times computational scientists come to computer scientists or they try to help out, and they've already fixed 8 of the 10 variables in the problem. The variable could be the abstraction, it could be how the data is laid out, it could be how big I'll scale, all of those things. And what a computer scientist needs is a multi-dimensional problem. And the more dimensions you give a computer scientist, the bigger the space of efficient solutions that can be imagined. And so knowing which parts of the problem are unchanging, right, that based on the physics, we really can't figure out another way to do this, and which parts are free to be constituted in some way is very important. I think the last thing I'll mention is that another thing that really helps this interaction between computational scientists and computer scientists over problems is thinking ahead of time, imagining what the paper you will publish together looks like. So if you approach it from the I'm your programmer perspective or you're their programmer perspective, there's no paper to be published, right? You're gonna write code for them. What do you write a paper about, right? If instead you meet with them and they say, and you talk about, let's figure out what your problem is, and then let's imagine a paper which is a new algorithm to solve this, or a new methodology for this, or exploring the performance characteristics of this thing. Now you've created a problem that a computer scientist is interested in, and vice versa. So a computational scientist can come to a computer scientist with those sorts of problems, where a paper could be published together, and then the computer scientist can think up answers in that space, can work on problems in that multidimensional space. So those would be my suggestions for how the two might, because I generalized it to how the two might work together more. So now the computational scientists will respond.
This has gone in a slightly different direction because I was going to make a whole bunch of rants about libraries and programming languages and stuff like that. But no, I think you brought up some interesting issues. So I forgot the orientation of your question about respect, because I feel like the people who get no respect are the computational scientists. We are the Rodney Dangerfields of, because, and I'm curious, I mean, you're on faculty at UW, right? Yeah. And you have something that's a pretty good deal, but you're not, so I'm curious your perspective on this, but I don't even pretend that I could apply for a faculty job. So I have a lot of people out there who are at universities who like me and give me compliments on my work, and I've had enough discussions with them where the chemists are like, there's no way in hell you would ever get a faculty job in chemistry at any university. And then my computer science colleagues like Pavan Balaji and people who have real CS degrees tell me, yeah, there's no way in hell you'd ever get a job in a computer science department, because I do, on a good day, second-rate computer science, probably most often third-rate, and I don't know jack about chemistry anymore because I forgot all of it. So, I mean, I feel like that one of the problems we have and why DOE is so successful in computational science, and I think academia outside of a handful of places like Urbana is generally unsuccessful at this, is because there is no academic home whatsoever for people who do what Jim and I do. There's no respect in academia for people who are essentially engineers of scientific algorithms and software. I can't even think of a compact term. The best thing somebody said, I was maybe a computer engineer because I understand blue jean hardware. But that's the closest I've gotten to maybe being acceptable to apply for an academic job. I think it's worth distinguishing a computational scientist from a scientist who uses computing, because I think of a handful of or the best 10% of all NAMD users as being computational scientists. But those guys, I mean, they can do science with one finger and a mouse, and I think what we do is sort of we are the interface between computer scientists and scientists who compute and computational scientists. So I don't know what category I even fit in anymore. But I think this is sort of one of the fundamental problems, is that we don't have a professional language of respecting each other to even work with it. So I consider a compliment when I get told at the MPI forum, not bad for a chemist, but that doesn't take me very far in my professional life. So anyways, but I guess maybe moving on beyond sociology, I think the comments that I thought of in terms of what do people who develop scientific software need from people who are computer scientists? The things that I do, so I look up a lot. I spend a lot of time looking at what's going on that's cool. I've downloaded and built probably 1,000 things, libraries, compilers, whatever, runtimes, apps in my, I don't know, I think that's a substantial number of things. People will say, have you heard of that? And I'll download and I'll build it. I mean, the basic thing is, if I can't configure, make, install, I just don't care. I will not suffer crappy build systems. I will not suffer stuff that can't compile with a basic Linux toolchain. So you guys don't have a problem with that, but for posterity I'll say, if you can't do software engineering, don't write software. And then I think beyond that, I mean, documentation, tutorials, simple examples are absolutely fundamental. There's computer scientists write papers for computer scientists the same way that philosophers write papers for philosophers. And then any philosopher goes out and writes a book for the general population, gets considered some sort of a hack or whatever. Any popularizer of science is sort of a dirty word. But I think to be a successful computer scientist that works with scientists, you have to sort of stoop to the lowly depths of making stuff parsable by people who don't, I mean, I told jokes at lunch about the halting problem, but I don't understand it really. For people who really have no clue about what all these formal, I don't know what N queens is. I can guess it has to do with chess, has to do with N queens on the chessboard, but they. Oh. But I think that as I said in my talk, some of the things that are wildly successful about some of these projects are actually the things that the computer scientists would poo-poo, and it takes people with a great deal of sort of brute force integrity like Bill Gropp to just say, no, this thing really, really will work and be practically useful, and I'm willing to, take a beating for it for not being, I mean, MPI and PETSI are amazingly successful because, Bill and Barry and other people have insisted that they actually work rather than do every awesome, crazy thing that you can imagine, cough, Trilinos, cough. So I don't know. I don't have much more than that.
Which computational scientists need from computer scientists? I figure the computer scientists can sort of fend for themselves. A little bit about myself. I sort of came to campus for grad school in physics, wanted to do theoretical physics back in '93, and math on the side and computers for fun, and ended up at the Beckman Institute. And you probably know this, but Beckman Institute is basically designed so that people from different disciplines can congregate in a neutral space and have offices together. So we've got chemists, physicists, psychologists, MDs, computer scientists, all sort of in this same space. So you're rubbing shoulders with people from different disciplines every day, and nobody is sort of in an alien environment. You're all, you all belong there equally. So I've been in Klaus Schulten's group for that time, and so we've got chemists, physicists, biophysicists, a few engineering computer types, collaborating with real experimentalists doing biomedically relevant experimental studies and getting funded by the National Institutes of Health, which is primarily interested in curing human diseases. So if you're talking about wanting respect, we've been sort of fighting for this field, the simulations we do, to have respect. And so we've been there, along the way. I've been through sort of this whole process, working with Sanjay's group, computer science, to get from point A to point B. So what have we learned along the way? Now I know Sanjay wanted numerical methods left out of this, but I'm just going to give you a quick pop quiz. What's the best way to invert a matrix? Yes, yes. There's almost never a need to actually invert a matrix. If someone asks you what the best way to invert a matrix is, you ask them what they're actually trying to accomplish. And this is basically rule number one for every interaction of someone coming into my office, work grad student, postdoc, whatever, asking for a very specific technical question. If someone asks you for technical assistance, figure out what they're trying to actually do. If what they are actually trying to do makes sense, then the other question is, well, okay, how do other people do this? Because you're probably not unique. So, there's no point in helping someone write code that already exists. There are lots of codes out there. There may be codes that don't do exactly the right kind of thing. And they may be better off just going off and using that. A few things that I don't think that computational scientists need. First of all, we don't really need computer scientists to write the code for us. Yes, I'm sure you could code very well, but I think it's easier to teach a physicist to code than it is to teach a computer scientist to do physics. Don't try to get us to write a specification. Don't try to understand the physics yourselves. Don't assume that we actually understand the physics. After all, it's research. And we may be working in one small corner of this field, but we're actually an expert in something else. Don't ask us to plan too far ahead. I read a great rant on the internet where someone's boss was asking, well, so what's your 2-year plan? It's like, I don't know. My boss is some cells in a Petri dish and rats in a cage. It's up to them where this goes. Science goes where it leads, so 2 steps ahead might be a little bit too far. So don't make your plans based on what we told you our plans are, because even if we think we know what we're going to do, that may not actually be the case. And don't ask us to learn anything more than what we need right now. One of the rules in doing science is, you can try and prepare, but it's best to just jump in and learn as you go. So, when you've got a real problem to apply something in, that's when you're most willing to learn it. And I think the most important thing is you don't want to be in a situation where a computationalist you're trying to help is dependent on you to fix something for them or explain something for them, or you're the only one who understands their code and you want to leave, and then they're stuck without this. So you really want to make sure that anyone you're working with ends up independent along the process and know what they're doing. Now, what do we need? Perspective, guidance, and feedback. And these are sort of in priority order. So when you're talking to someone, in physics you're learning mathematical methods, in chemistry you're learning all sorts of stuff. All the basics of computer science and software development education, this doesn't come up. So, choosing efficient and scalable algorithms. People don't even know what they need. They write something, it works. So it takes 2 hours. I had a grad student actually who was, he was writing some code in MATLAB, and it took forever. And then he tried C, and he was really happy. And it only took like 20 minutes to run. And then he discovered -O, and boy was he thrilled. So really basic things. So source code revision control. You don't come across this until you see someone else using it. So, this is RCS, this is CVS, this is Git. Automating building and testing, using existing libraries for things rather than rewriting them. This is how the rest of the world does matrix algebra. Use LinPack. Use these other things. Writing legible code. People are used to doing a homework assignment, turning it in, versus you write software. If they can't explain it to you, they're not going to understand it when they come back in a year. That's something that it's better to learn from other people's experience than your own. How to write code that's extensible, how to make code portable rather than something that works on the one machine. And finally, all the way down at the end, actually making that code efficient and scalable. These are the kinds of things that you have expertise in. And one thing I learned in grad school, people are nervous about being a TA, and they come back on the first day, and it's like, however little you know about your topic, the students know less. So however little you know about software development and coding and algorithms, the computational scientists who have spent all their time learning physics, chemistry, biology, they know less than that. So this is what I call rule number 2 for teaching assistants. Who remembers rule number 1 from TA training at the University of Illinois? It really didn't come up in physics, and I'm guessing not computer science that much, but we spent like 2 hours on don't date your students and how to deal with the girl who will do anything for any in this class.
Don't computational scientist, is that?
I think this transfers, but it might be good to bring in some humanities. And my wife was a physics major, but she's a librarian now, so it spreads out a little bit. So some other things that we don't need, we do need tools, but we don't need tools that make simple things easy. If you can understand how to do it in 5 minutes, you don't need a tool to do it in 2 minutes. Especially if they don't support the hard things. So you start using this and then you get stuck. And the problem with that is, and we've had this same issue in the software. It's like, why can't we make this all really simple? Well, the problem is, when people are learning the software, you want them to be learning how to do progressively more complex things with the software. And if you make everything easy up to a point, as soon as they hit that point, they hit a brick wall that seems unsurmountable. Whereas if they've been climbing the hill for a year, it's just another step. So don't come up with tools that are going to give people learned helplessness. Tools need to be, can't be single purpose or limited purpose. They have to work with algorithms, multiple algorithms in an application, and every time there's another library that I have to fold into NAMD, that makes it harder to build the software on a new system. That increases the odds that it's going to be less portable on that system, especially if that library doesn't get ported to a particular new platform. So, keeping it simple is good. So what we do need, again, is the tools have to support incremental progress. So they should have a minimal interface that's complete, and the 2 rules from training dogs and people are you want to reward every improvement and reward any improvement. So if people are going along with using the tool, they should get some improvement along the way, as opposed to you do all this work and then at the end of a year you find out what you get. For exploiting existing tools, I think it's important, not so much to produce new tools as to figure out the best ways to use the tools that we have. So for example, design patterns are great. They tell you this is a software solution to this class of problems. If those are provided with example implementations that people can copy, that's very useful. If you think about the evolution of C++ with templates and template metaprogramming, when C++ first came out, it was very basic, but it had this templating structure, and people started doing stuff with it that was a little bit hard on the compilers, but completely within the structure of the language. And that's taking an existing tool and building something on top of it. What we don't need so much, again, are proof of concept tools. If you've used something for one application, you haven't proven anything. You've just done one test case. Tools that not a lot of people use are not that much fun. It's not fun to be the only person who's finding bugs in code, which is why I'm glad there are lots of projects using Charm++. And finally, eat your own dog food. So if you've got a tool, you should have something that you're using it for your work every day. And sort of my one little personal gripe is, there are a lot of load balancers in Charm++, but most of them are serial. And if only there was a convenient language we could use to parallelize these load balancers so they could run faster, that was, adaptable and dynamic and made life easier. So
I asked a series of groups. I asked a series of companies. Which of the companies had written their
OpenMP compiler in OpenMP, and none of them had. And then they asked me, well, why would we do that? They didn't even grok the necessity to write your OpenMP compiler in OpenMP. Anyone else?
they didn't say because it was buggy.
No.
But yes, so what we do need are tools that we can trust, and that trust means, if I use this tool, will it work across platforms, across machine sizes, problem sizes, and for the lifetime of the code. And the lifetime of the code may be 1 year for an undergrad, for a master's thesis, or it could be decades. And the reason trust is important is not just because we want to get along well, but it really changes the dynamics of how you work with software. So if I'm using something and I don't believe that it's well tested and bug free, then when something doesn't work, I'm going to blame the tool that I'm using rather than looking through the code that I've written to try and figure out what's wrong. So I've sort of used CUDA back in the early days, and there were plenty of things that you would not expect a sane compiler to do, and I to this day have a hard time trusting some of that work. And then I'm shipping code that 50,000 people use or whatnot, and if I don't trust the tool, or if something in the tool breaks something in the code, if they don't trust that NAMD is working well, then if there's a problem, if their machine is flaky, or if there's something wrong with their hardware, or if there's something with their input, then they start questioning the code rather than looking for where the problem likely is. And when the users don't trust the software, then support becomes this nightmare of finger pointing that is very important to me to avoid, which is why everything that goes out as NAMD is as bug free as I can get it. It's not because I really don't want the users to suffer. It's because I don't want to suffer trying to explain to users, no, the problem's over there, look again. So in summary, do ask deep questions, but don't try to do our jobs for us. Do give basic advice, but don't try to make simple things trivial. Do support incremental advances so people can use the tools at whatever level makes sense. Don't build toys, and do earn our trust. Thanks.
Right. So somebody mentioned yesterday that I'm the graying beard here. So my beard is turning gray, so I thought I'd be the one to give a little bit of a historical perspective on this. What have, particularly in the history of computational astrophysics, and give just a couple of historical examples of how computational scientists, computational astrophysics physicists have worked to great good with computer scientists. So I'm going to go way back. Probably everybody knows the person, this person. Sanjay knows who it is. So that's Johnny von Neumann. Okay. You probably won't recognize this gentleman. His name is Martin Schwarzschild. He was I knew him as a professor at Princeton. You've probably heard of the Schwarzschild radius for a black hole. That's actually his father, Carl Schwarzschild. So this is the son of Carl Schwarzschild of black hole fame. His noted accomplishments in astrophysics include the structure of stars and the dynamics of stars as they move in galaxies. These two gentlemen first met each other at the Aberdeen Proving Ground during World War II. He was working on trajectories, what they called external ballistics. And you can guess that this gentleman was working on what they called internal ballistics, the fact that the shock wave from the bomb going off was the thing that caused the most destruction, not the fragments. And so we have, von Neumann, Richtmeier viscosity, all the numerical methods with modeling shock waves starts with his work. But when they were both at Princeton, he was at the Institute for Advanced Studies, and he was over in the astronomy department. And he was doing these calculations of stellar structure. It was, your quote, the physics of the stars had finally been worked out in 1948. That is, the nuclear reactions that powered the stars. And so he could start building models of stars from the nuclear reactions all the way out to how bright it is at the, the luminosity of the stars at the surface. And I might as well, let me finish the story here. But this involved a coupled set of 4 differential equations which had to be integrated from the surface. And furthermore, it was a boundary value problem. That is, we knew, the luminosity was 0 in the center of the star, and it was the star's luminosity at the start. And so he had to do the shooting method for calculating the trial and error to get a solution for a star. And he was doing that using a desk calculator, crank run, and he figured out that he could go across campus and start using this guy's computer, which was a bear to use, right? Did not have floating point arithmetic. There was there was no error correction. Right? You had to make up these paper cards to feed into it. If something broke, usually a vacuum tube would break, and so that required cutting away the wires so you could get at the vacuum tube, replace it, and then solder the wires back together. And so there were long periods of time when this computer was unusable. Nevertheless, this gentleman learned quite a bit about computers from Johnny von Neumann, and a couple of lessons he learned. So this is going back into the 1940s, and so this concept that the computer memory could also hold a program was just wild, although it was very obvious in retrospect. But when they were thinking about, at that time, the electromechanical computers, putting the program in the memory was this very strange thing. There's some controversy whether von Neumann actually first thought of that. But nevertheless, this was a computer science concept that Martin Schwarzschild learned from von Neumann. The if statement. Wow. And again, the idea that you could control what instruction you loaded next based on a conditional test was this new concept that Martin was unfamiliar with, Professor Schwarzschild was unfamiliar with, and von Neumann familiarized us with him with that. And then this method for solving a boundary value ordinary differential equation, where you start at one boundary, integrate to the next, and try again until you match the boundary condition. About that, this was in the late 50s, a new algorithm came up where you actually do an iterative solution. That is, you do finite difference equations at multiple points between the two boundaries, start with a trial solution, and then attempt to come up with by iteration, come up with a self-consistent solution across the problem domain. That originated, it's unclear how much von Neumann contributed to that. But certainly on the Princeton campus, this was discussed, and it eventually became known as the Henyey method for solving stellar structure, which is the standard way everybody solves stellar structure today. Okay, so that's 30s and late 50s. Let's jump ahead 20 years to these gentlemen. People know him?
So this is Andrew Apple.
Currently professor at computer science professor at Princeton. This gentleman is Jerry Sussman, MIT professor. And these people, you might not recognize their faces, but their names will be very familiar. This is Joshua Barnes. This is Pete Hutt. Okay, so these two gentlemen are gravitational dynamicists. They were interested particularly in the movement of stars in globular clusters. But they had a problem that the standard method for solving Poisson's equation usually involved like FFTs, which were nice if you had a cubical problem, but globular clusters are not cubes. Okay, so it didn't really work for them, and they wanted an efficient technique that was not so dependent on the problem geometry. A few years before, and I think as an undergraduate, Appel wrote a tree code for solving gravity under the mentorship of a physicist, Jim Peebles. I'm not sure exactly what the communication was here, but his code was really unworkable because although it was a tree code and it was efficient in solving gravity, he didn't, being a good computer scientist, he felt like he shouldn't rebuild the tree very often. And so his code, the tree would get tangled up and become very inefficient very quickly. These gentlemen, I think they knew about this, but they had the recognition that actually rebuilding the tree every time is not such a bad idea. And so they have a very simple tree that was quick to build and became, as you know, very widely used solver for the gravitational n-body problem. Furthermore, expressing the tree build in, say, Fortran was not so easy, and that's where this gentleman came along. You know, he's one of the designers of Scheme, which is a language where recursion is the standard way to express iteration, even. And so these gentlemen learned about recursion, and so were able to easily express their tree code in a C program. Again, what did these people learn? So first of all, non-trivial data structures. New ways to describe data is something that they learned, and also this new concept of recursion that at that time was not very familiar. In fact, Fortran essentially expressly forbid recursive function calls. And then there was another part that came out of that. Pete Hutt was also was a founder of this work called the GRAPE hardware, so the gravity accelerator. And I think he picked up a lot of this from Jerry Sussman, who was trying to convince a lot of us that astronomers could actually build their own computer. What I have down here should be a little bit bigger. So this is digital orrery, built back in the 80s. It's a rack of 9 cards, 1 card for each planet, with a bus connecting them. Well, not a bus, but interface so that each card could pass its position to the next card in a round-robin sense. And calculate gravity. And they use this thing to calculate the orbits of the planets over a billion-year time scale. It was a record for the time in which they made the remarkable discovery that the solar system is unstable in a certain technical sense. And so that was quite a groundbreaking scientific work that was based on computer scientists convincing somebody that you could actually build a computer to solve your problem. And then Pete Hunt and joined up with the Japanese folks, Makino is the name I'm trying to remember, to start the GREAT project, which had great progress over the years. It might be superseded these days by the GPUs, but nevertheless a great contribution to computational astrophysics. So, I mean, I feel too modest to put my picture and Sanjay's picture up there, but just in summary, a couple things. Learning, teaching us abstractions that you folks are finding are useful for computational science. New algorithms. Okay, a lot of the advances in computational algorithms have been brought about by the application of these new algorithms, and teaching us. I don't know if I want to go there, but I still need to know what the hardware constraints are. And indeed, I've just been told today maybe I should think about becoming more like Martin Schwarzschild and giving up the floating point unit. Maybe that, but I'm just using that as an example. You guys know something about where the hardware limitations are that will eventually, that should inform us of how we ought to do our astrophysics. Okay.